So I'll be talking about error correcting codes for uncompressed messages, which is a paper by Ofer Grossman and Justin Holmgren. So let's start by introducing the setting we talk about. And the setting is very similar to the standard error correcting code setting. So we have two people, Alice and Bob. And Alice wants to send some message to Bob. For example, suppose she has some image she wants to send to Bob. And unfortunately, their channel is not perfectly secure. Let's say that on this channel, there exists some adversary. And let's say he can corrupt up to 3% of the bits on this channel. Right, and this 3%, of course, we can change it, but just to be concrete, let's assume it's 3%. And let's assume the adversary is worst case. So in our setting, we're going to assume he's worst case, meaning he's computationally unbounded, and we'll assume Alice and Bob are bounded. Let's say they're polynomial time. And so what can Alice and Bob do in this setting? So there's kind of a classic solution, right? So first, what Alice is going to do is she's going to compress her message as well as she can. And then she's going to use an error correcting code to send the compressed message to Bob. Right, so first, of course, she wants to compress, right? If she can compress in a lossless way her message to something half the size, then later when she uses the error correcting code, she's going to send half as many bits to Bob, so she can save on bits. So the better her compression is, the fewer bits she's going to have to send to Bob. And then the next thing is she's going to want to use an error correcting code. Right? So an error correcting code is just something that allows that even after certain errors, certain bits of the message are flipped, Bob can still recover the original message. All right? Cool. And so our work starts by looking kind of at this setting. And something we notice is that instead of viewing this compression error correcting code as two kind of individual separate steps, we can kind of think about them together. Right, so you could imagine that, for example, doing the compression error correcting codes together allows you to do things faster or achieve better rates, right?
It's worth noting that in the case that Alice and Bob are unbounded, then Shannon proved that first doing compression and then error correcting code is in fact optimal. But when Alice and Bob are polynomial time machines, like they are here, then it's different.
So for example, you might have some type of data, for example, or an image, where you don't know how to compress that well. But when you view compression and error correcting codes together, you're able to get much better rates. So the idea is, instead of viewing compression as a problem and error correcting codes as a problem, we view kind of for what types of data can we do these both together, and see for what types of data we can achieve something better by doing them both together instead of doing one and then the other. So that's kind of at the very high level what the idea is. So let's be a little more concrete about what we mean by an error correcting code for an uncompressed message. So first let's just write down the definition for a normal error correcting code in this setting, right? So an error correcting code is going to be a pair of an encoding algorithm and a decoding algorithm. So an encoding algorithm, a decoding algorithm, so that for every message, let's call it M, when I decode the encoding of the message with some errors, I get the message again. We want to assume that there's at most 3% errors. Right, so that's what an error correcting code is. Whenever I take a message from this message space and I encode it and add errors and decode it, I get my original message. Cool. And when we deal with this, something we often care about is the relationship between the size of E of M and the size of M. So between these k bits that it takes to write down M and how big the encoding is. And so with this in mind, let's write a slightly different definition. So a slightly different definition is an error correcting code for a set S. This is also going to be a pair of an encoding and a decoding algorithm. So for all messages in S, when I decode an encoding of M errors, I get M. So let's compare this new definition, error correcting code for a set S, versus the standard definition for an error correcting code. So the main difference is that over here, we wanted every message in 0, 1 to the K when it's encoded with errors and decoded to get the original message. Over here, we only want for messages in S to be properly decoded. So we can imagine S as some subset of 0, 1 to the K. So we can think, for example, of S as the set of all, for example, valid images. So suppose we know Alice wants to send Bob an image, right? Maybe Alice is texting Bob an image. So we know she's sending some image. So here the guarantee is for any valid image, when I encode it, add errors, and decode, I get M. So maybe one way of thinking about it is if S is all the set of valid images, so anything that looks like an image is in S, and everything that looks like just random gray noise, just like a random array of like random pixels, is not in S. So in this new definition, our guarantee is whenever you send an actual image, right? Whenever you send, like, for example, a picture of something that looks like a dog, then you encode it, add errors, and decode, and you get the original thing. But there's no guarantee over if you send like some random array of like pixels, there's no guarantee. And that makes a lot of sense because Alice doesn't actually care how her error correcting code behaves on random arrays of pixels. What she cares about is how the error correcting code behaves on images. Right? Or, similarly, if she's sending some audio, an audio file, she doesn't care about how the error correcting code behaves on just like random white noise. What she cares about is how it works on actual audio. Or if, she's sending some English text, she cares about what it looks like when you send English text and not what it looks like when you keyboard mash random characters. Great. So we can view this new definition as a relaxation of the old definition, where we don't want a guarantee on all messages. We only want a guarantee for messages inside the set of kind of reasonable messages S. So S is like the set of reasonable messages of messages that it's plausible that Alice might send. And we only want a guarantee over those messages. Cool. Great. So with this new definition, the next thing to do is to kind of ask, well, what can we achieve? What does this definition allow us to achieve? So let's write down a theorem statement. So write it down and then we'll discuss it. Okay, so here's the theorem statement. So it's telling us that for every polynomial time recognizable set S, where S is small enough, there's an error correcting code for up to 3% errors where the size of the encoding is 1.74K. And in a second, we'll talk about the exact rates, right? So roughly the way I think about it is whenever I have an S that's polynomial time recognizable and small enough, I have an error correcting code for S that's much better than just encoding the whole space 0, 1 to the K. So kind of naively, if you have some set and you don't know how to compress it anymore. You've tried compressing, but either you don't know or you don't have the computational resources to compress it. But the set S is still very small, right? So information theoretically, I could have compressed it to size K over 2. So information theoretically, I could have compressed it, but maybe due to computational limitations or because I don't know the right algorithms, I'm unable to. So in that case, as long as S is polynomial time recognizable, I can encode it and get much better rates than if I just, did the naive thing of encoding all of 0, 1 to the K. All right, cool. So let's look at this a little more in detail. For example, let's look at this polynomial time recognizable thing. So polynomial time recognizable just means that given a string in 0, 1 to the K, you can within polynomial time and K tell me if you're an element of S or not. Right? So you can think For example, let's think again of S as the set of images. So here we would require that there's a polynomial time algorithm for recognizing if something is an image, right? So in practice, like I imagine this doesn't exist, but you can use like a heuristic algorithm for checking if something is an image or not, and then set S to be the set of things that pass this heuristic algorithm, right? And then furthermore, we want S to be small. And this makes sense because if you look at the set of all grids of pixels, very few of them are actually valid images, right? So the set of valid images is going to be very small compared to the set of all, grids of pixels. Or if you want to think about S as the set of all valid English text. So suppose Alice wants to send English text, right? Then 0, 1 to the k would represent all strings of a certain size. And S would just be the strings that actually make sense as English, that don't look like just keyboard mashing gibberish. So then S is going to be very, very, very small, right? Because if you just keyboard mash, the probability that you'll get an actual English, something that makes sense in English, is going to be extremely, extremely small. And we assume there's a polynomial time recognizable way of doing it. All right, great. So for these, there will exist an error correcting code where the encoding of the message is of size 1.74K. And to compare it, let's compare it to what we could have done otherwise. So suppose we have the set S. We tried compressing it, but we're unable to. Maybe because we don't have computational resources, maybe because we don't know the right algorithm. There's a bunch of reasons why we might not be able to compress it. But just knowing its size and knowing that it's polynomial time recognizable allows us to guess 1.74K. If we didn't have this idea of creating an error correcting code just for S, we would be stuck in trying to find an error correcting code for all of 0, 1 to the k, right? So the naive thing to do, if you don't know about this idea for finding an error correcting code just for S, is to find an error correcting code for the whole space 0, 1 to the k. And if you find an error correcting code for the whole space 0, 1 to the k, the best you can do before work is 2.52k as the size of your encoded message, or 2.27k as the size of your encoded message. Right, so 2.52 is the best known before our work, and our work actually, as kind of as a corollary of this stuff, creates better randomized codes that are efficiently decodable and encodable. So with randomized codes after our work, you can lower it down to 2.27. But either way, it's higher than this 1.74 of when you just look at S. So that's the idea. And of course, in our paper, it's not like specific to 3% errors in this size, but there's this whole trade-off between size and amount of errors and all that. And it's kind of a mess to write down what this exact trade-off is, and it depends on prior works, because what we do is we build upon like previously constructed codes. So if you want to know the exact details and trade-offs, you can look at the paper. But I think this example of parameters kind of highlights what's new, and you can just imagine how things change when you change the errors, when you change the size of S, and so on. Cool. And so let's just give a quick idea of how we construct these things. So kind of a proof sketch. So proof sketch. So the idea is to use list decoding. Okay, so some of us might know what list decoding is, but let's give a quick intro to list decoding anyway. So list decoding is similar to normal error correcting codes, where I take some message and I encode it and add errors, and then I decode it. And then usually in normal error correcting codes, I would just get my message M. But over here, it's a little different. I'm going to get a list of messages, M1, M2, M3, up to polynomial size. Let's call it MS. Cool. So I get some list with the guarantee that at least one of these messages is M. So M is somewhere in the list. So that's the idea. And why do we like list decoding? Because we get better rates. So if you want unique decoding, you're going to get worse rates than if you're okay with list decoding. So if you're cool with having a polynomial sized list of options where one of the options is your real message, then you can get better rates. This is our starting point. And so here's the idea. Suppose Alice takes some message and sends it over to Bob, and at the end you get a list. Kind of, if she's lucky, what's going to happen is, of course, the message has to be there. And then there's going to be some other strings, right? Cool. You could imagine this is the list. So if you got a message, you decoded into a list, and you got this list, you can kind of be pretty confident that these two weren't what's meant, and hello was the message that was actually meant. The message that was actually sent, right? You look at it, you see two things that are gibberish and one thing that makes sense, and so you know it's the thing that makes sense, right? Or imagine, you get a big list of images. One of them is a picture of a dog, and then there's 99 pictures that look like random gray static noise. Then you can be pretty sure that it's the dog that was the picture that was meant to. So that's the idea. So the idea is, if we can augment list decodable codes to make sure that they behave in this way, then that would be great. So of course the problem is, right, something that would be bad if in this list there was another reasonable message, right? Another message in S. That would be bad, right? So our work can, at the high level, can kind of be viewed as making sure that with high probability, we create these list decodable codes so that with high probability, in the list, there's only going to be one element in S, one element that looks reasonable. Right? So formally, we want one thing to be an S and everything else to not be an S. Cool, so that's the idea. And going a step further, the way we kind of do this is we create a pairwise random permutation. We can permute the messages and then encode them using a known list decodable code. And then you can check that if this known list decodable code has certain good combinatorial properties, you can analyze it and show that with high probability over the choice of the pairwise independent permutation, everything works. And with high probability, whenever you encode something with S, your list will only contain one element in S. So that's the idea. And I think the main thing I find interesting here is kind of this idea that within error correcting codes, you don't have to think of your input space as just 0, 1 to the K or some alphabet to the K. But in general, you can think about encoding sets in general. And it turns out that you can get some sort of interesting and also pretty general things about S's. For example, if your S is small, then you automatically get much better codes than encoding the whole space they're in. And I imagine within error correcting codes, there's probably more interesting things to do with this. It's also interesting that like using these techniques, you can get better randomized, efficiently decodable codes than were known before. And yeah, maybe also outside of error correcting code, this idea of looking at your input not as from 0, 1 to the K, but coming from some specific small set within it could be interesting, because in practice, a lot of our data isn't actually drawn from like 0, 1 to the K, but is drawn from a very small subset of it. Like if you're doing image analysis or whatever, I keep using this image example, but a lot of types of data are actually, they're not coming from something that's 0, 1 to the K, but they're coming from something much smaller. And maybe that can give speed ups, better rates, and who knows. So yeah, thank you.